Hello everyone, welcome back to Knock Knock Your Education, and I hope all of you are doing good. So this lecture is in continuation to the lecture which I gave you on matrix representation of linear transformation. So in this lecture we will be doing a few questions on for the purpose of practice. So let's get started with the questions. So today what we are going to do, the questions are, the first question is, you have been given a linear transformation D be a linear transformation such that D is from P2x to P2x, and I hope all of you knows about P2x. P2x is nothing but the collection of all the polynomials whose degree is less than or equals to 2, and it is defined as, for any polynomial in P2x, it maps it to its derivative, that is dp by dx, and the basis that is being given to you is 1x and 1 minus x to the whole square, and with respect to this basis you need to find out the matrix representation of this linear transformation D with respect to the basis B. So again, the process is very simple, and we just have to use the general method that we know, that you just need to find out what the what we say is that the linear combination of the basis members. So if you are going to evaluate D of 1, so derivative of 1 is 0, so obviously I can write it down 0 into 1, 0 into x, and then plus 0 into 1 minus x whole square. If I evaluate D of x, it is going to be the derivative of x, so that is 1. So I can very easily write it down, what, 1 into 1 plus 0 into x and plus 0 into 1 minus x whole square. Next we have D of 1 minus x whole square. Its derivative is going to be 2 times 1 minus x, but here one more thing, we have to do the derivative. So after power we have to do the derivative of this function. It is minus 2 times 1 minus x, so this is minus 2 plus 2x. So I can write it down, minus 2 into 1 plus 2 into x plus 0 into 1 minus x whole square. See, the process is so simple that we learned in our last class, and we are just doing all those things on behalf of that. So the matrix representation of D with respect to this basis is nothing but the transpose of the matrix, coefficient matrix, that is 0 0 0, and then we have 1 0 0, next we have minus 2 2 0, and then we just have to take the transpose. The final answer we are getting is 0 0 1 0 0, then we are getting minus 2 2 0. This is the final answer for this question, that if we want a matrix representation of this linear transformation from P2x to P2x, which maps every member of P2 to its derivative with respect to this ordered basis, the matrix representation is this. So I hope the question is clear to you, and this was a very simple question. You just have to go through the general method that we discussed in our last class. So the next question that we will be discussing today is this question number 2 that we will discuss. Again, we are considering D from V to V as a linear transformation, where D of P of, suppose this is P of T, this is going to where but dP by dt, and here the basis that is being given to you is sine t, then you have cos t and e raised to the power t. So here we are considering as the collection of functions from that is from V to V, a D where V is a collection of all the functions. So basically we are just taking a subset of this V, where we have sin t, cos t and e raised to the power t. We have been given like this, not specified, but V is a subset of the collection of all the functions. So here we need to find out the matrix representation of D with respect to basis B. So again we will follow our general method, and what it says, we will find out the images of what basis members, and then we will write them down in terms of the linear combination of the basis members. So derivative of sin t, as all of you know, is nothing but cos t. So this is going to be 0 times sin t. As I told you, this is an ordered basis, you cannot change the order of the element. This is 1 time cos t, and this is 0 times e raised to the power t. Then you have to find out d of cos t, which is nothing but d by dt of cos t, and this is your minus sin t. then this is going to be minus 1 times sine t plus 0 times cos t and plus 0 times e raised to the power t. Then d of e raised to the power t, that is derivative of e raised to the power t, this is e raised to the power t, this is going to be 0 into sine t plus 0 into cos t and plus 1 into e raised to the power t. So the matrix is going to be the transpose of the coefficient matrix. So 0 1 0, this is the matrix which we are going to take transpose. So I am directly writing down after taking transpose, this is 0 1 0, then we got minus 1 0 0 and then we got 0 0 1. This is the final matrix for this linear transformation with respect to this ordered basis. So these are the questions which are based upon the subspaces of the vector space containing all the functions. This was the P2x set, that is containing all the polynomials of degree less than equal to 2. Okay, so let's discuss another question. So the next question that we have to discuss is t from R2 to R2, and t of x comma y is being defined as x plus y comma x minus y, and the basis that is being given to you is 1 comma 2 and minus 1 comma 0. See, I have already told you, if you want to practice these questions, you can pause the video after noting down the question, and then you can write down your own solution, then watch my solution and cross check whether the answer that you are getting is similar or not. Okay, so as I have told you, you can take a general member of R2 and you can write it down in terms of linear combination of the basis members, because we don't want to solve the system twice. So what it would be, this is 1 2, then we got minus 1 0 and xy, or similarly you can get 2c1 equals to y. So you will get from here, you are getting 2c1 equal to y, that is c1 equals to y by 2, and this is your c1 minus c2 equal to x. So your c2 is going to be c1 minus x, yani y by 2 minus x. So what you can do here is that you can write it down your x comma y member as y by 2 times 1 comma 2 plus y by 2 minus x times you are getting as minus 1 comma 0. Fine, this is what you are getting. Now what you can do is that you can take the image of the basis members t of 1 comma 2 according to this definition is x plus y, it means 1 plus 2, that is 3, x minus y, it means 1 minus 2 minus 1. Okay, then you can get t of minus 1 comma 0 as, this is your x plus y, it means minus 1, x minus y, again this is going to be nothing but minus 1. So by now we will use this definition. So this is y by 2, it means minus 1 by 2 times 1 comma 2, then y by 2 minus x, it means minus 1 by 2 and minus x. This is minus 1 by 2 and this is minus 3 minus 1 comma 0. And here what we have again, this is y by 2, it means minus 1 by 2 1 comma 2, then this is y by 2 and this is minus x, so this is going to be plus 1 minus 1 comma 0. So overall we got t of 1 comma 2 as, this is minus 1 by 2 times 1 comma 2, then we have minus 7 by 2 times minus 1 comma 0, then we got t of minus 1 comma 0 as minus 1 by 2 times 1 comma 2, and then here we will get minus 1 by 2 plus 1, that is 1 by 2 times minus 1 comma 0. So we know that we will take the transpose of the matrix. So what we are getting, minus 1 by 2 minus 7 by 2, then again we got minus 1 by 2 and 1 by 2. This is the matrix that we are getting for this question. And see, one more important thing is that in this question, if I would have asked you to find out the matrix representation with respect to the standard basis, okay, if this linear transformation remain as it is, and if I would have asked you about what, about the standard basis, if I am giving you and I asked you to give me the matrix representation, then you can use that trick which I taught you in the last class. You can simply tell me that the first component represents the first row. So component first component is x plus y, coefficient of x, coefficient of y, and then the second component will give you second row component, coefficient of x and coefficient of y. So this is the matrix that we are getting. Fine. And let's discuss another question, and this another question, let me tell you, is very important, because this is one of the very special case that we are going to discuss, though I will tell this question to you in change of basis also, but still I am discussing it here. And what is this question? Suppose I am giving you now matrix. I am telling you to find out a matrix representation of a linear transformation, but this is not a linear operator. See, this is from one vector space to another vector space, and both the vector spaces are different. So here the mapping that is being defined is like this: t of x comma y comma z as 1 comma 1. Sorry. This is going to be your x plus y minus z, comma, this is your x plus y plus z. And now you think from the previous lecture what we studied, what we were doing is that since there the vector spaces are same, we were working on linear operator. So हमारा काम सिर्फ एक बेसिस से चल जा रहा था. क्यों? बिकॉज वी हैव same vector spaces. So this is the basis for this one also, and this is the basis for this one also. So what we were doing, we were just finding out the images of the same basis, and we were just writing it in the linear combination of this basis only. Okay, but here this concept cannot work. Why this cannot work? Because this time we have two different vector spaces. So the basis of V may not be the basis of W. So here we will need two bases. But the concept that we studied will remain same. What? Suppose this is your V1, V2 and Vn. Say this is n dimensional and this is m dimensional. And this is, suppose you are saying this is U2, U2, Um. Fine. So again the concept is same. You will find out the image of B1 and you are going to represent it in terms of what? In terms of U1, U2 up to Un. So the basic concept remain as it is. Fine. So don't panic if sometimes this kind of question comes in front of you. If this is not a linear operator, just apply the basic concept that we studied. So that is why I am giving you one question on behalf of this concept as well. And I'll give you one question as a homework also. And in the last lecture I gave you one question for the homework, and there was something which I wanted to discuss about that question, but in the next session I will discuss that, so that few more of you can see about this question and see what is the problem. Okay, so let's discuss about this question. We have a basis B1, that is 1 1 1, then we have 0 1 1 and then 0 0 1. This is the basis for R3, and we have a ordered basis for R2 as well. And what is it? 1 0 1 1. So now you see one thing. If I am calling these members as V1, V2, V3, and I am calling them as suppose U1, U2. So you know that T of V1, then T of V2 and T of V3. Where do they belong? Obviously these are the images of V1, V2, V3. So they will belong to where? R2, right? Because your V1, V2, V3 are belonging to where? They are belonging to R3. So their images are belonging to R2 according to the mapping that is being given to us. So you want to write it down. What you want to write down is that the images of V1, V2, V3 as the linear combination of B2 members. So again, don't solve the system once, twice, thrice. Do one thing. Take a general member x comma y. Write it down like the linear combination of the B2 members. Okay, U1, U2. So here what you are getting is C1 plus C2, and here you are getting is what? C2. This is your x comma y. So you got C2 equal to y, and from the equation C1 plus C2 equal to x, you got C1 equal to x minus y. So you can in general write down a member x comma y as x minus y times 1 comma 0 plus you got y times your 1 comma 1. Okay, this is what you are getting. Now it's time to find out the images of V1, V2, V3. So you need to find out TV1. This is your T of 1 1 1. And now which definition you are going to use? the definition that you are going to use is this one, that is x plus y minus z. So this is 1 plus 1 minus 1, this is 1. This is x plus y plus z, this is going to be 3. Fine. So next you have t of v2, which is t of 0, 1, 1. So again you have x plus y minus z, that is 0 plus 1 minus 1, this is 0. And this is x plus y plus z, this is 2. Then you got t of v3, which is t of 0, 0, 1. So that is going to be x plus y minus z minus 1, and then you need to add all the 3 components. Here you are getting 1. Fine. So now in the next slide I am going to write them down as a linear combination of the B2 members. So just let me write down all the important things over here. X minus y, you got 1 comma 0, and then you got plus y times 1 comma 1, and then you got t v1 as what, 1 3. Then here you got 0 2, and next you have minus 1 1. Okay, minus 1 1. This was your t of v2 and this was your t of v3. Okay, and these are, you know, your u1 u2. So now you can write them very easily in terms of u1 u2. This is x minus y, so this is minus 2 times 1 comma 0, and this is y, so this is 3 1 comma 1. Then x minus y minus 2, again 1 comma 0, 2 times 1 comma 1. X minus y, that is minus 2 times 1 comma 0 plus 1 time 1 comma 1. And I have told you in the previous class, whenever you need to find the matrix representation, you have to take the transpose. So this is minus 2 3, minus 2 2, and minus 2 1. You will take the transpose, and the answer that you will get is minus 2 3, minus 2 2, and minus 2 1. Okay, so this is also very predictable from here, that I am telling you one thing. If you are getting t from a vector space V to vector space W, where dimension of V is your n and your dimension of W is m. So whenever you are getting a matrix representation for this linear transformation T with respect to, you know, B1, B2, B1 is the basis for V and B2 for W, then this matrix is always going to be of order m cross n, where m is the dimension of W and n is the dimension of V, always from here to here, m to n. So suppose if you are getting a matrix of order 3 cross 2, again you will say that this is wrong. Why? Because 2 cross 3 is going to be the order. This is what the matrix we are getting. Fine. So this type of question was also very important for you, so that you can understand that if in exam we are not getting any linear operator, at least we are able to find out the matrix representation of a non-linear operator also. From here we will study one more concept. Okay, let's see what is that concept, and with the help of question I am going to tell you. Suppose you have been given a, you know, linear transformation or linear operator from R2 to R2, and this time you have been given that B is the standard basis of R2. Okay, B is the standard basis of R2. So आप लोग को आइडिया लग ही गया होगा क्या होगी ये. This is going to be 1 0 and 0 1. Okay, and this time you have been given a matrix representation with respect to the standard basis only. And what is this? This is given to you as 2 3 minus 1 2. Okay, and अब आपको पूछा गया है find the LT, that is find the linear transformation, that is the definition of linear transformation, how it is mapping the element of R2 to the R2. See, there are two ways for this question. The first one is what I taught you as a trick, and the second one is what I taught you as a basic concept. First, I am giving you with the help of the trick. I told you whenever you have been given a, you know, linear transformation, ठीक, fine, if we are talking from V to V, एंड स्टैंडर्ड बेसिस के रिस्पेक्ट में अगर हमको कोई भी चीज़ बोली गई है, तो आई टोल्ड यू कि फर्स्ट कंपोनेंट जो होता है वो आपको फर्स्ट रो देता है, सेकंड कंपोनेंट जो होता है वो आपको सेकंड रो प्रोवाइड करता है. बस इसी ट्रिक को वी विल यूज़ एंड वी विल गेट आवर आंसर. फाइन. What is that? I told you that the first row will give you the first component. So don't you think so? T of x comma y, we will write down y because it is from R2. So the first row will give you first component, right? And this was the coefficient of x, this was the coefficient of y. So we are getting 2x plus 3y. Then I also told you that the second row will give you second component. This is the coefficient of x, so minus 1 into x, which is nothing but minus x, right? This is minus x, and this is the coefficient of y. See how simple it is. We got our linear transformation. And if you have any doubt, आप इसको reverse direction में लेके जा सकते हो. यहाँ से यहाँ अगर बनाना होता तो I have told you ना, first component will give you first row 2x plus 3y, coefficient of x, coefficient of y. Second row will give you second component will give you second row. So this is coefficient of x, this is coefficient of y. तो आप tally भी कर सकते हो, whatever you are doing is correct or not. Okay. Now coming to the another way कि what we have studied through our basic concepts, we will try to solve it that way also. How come? I told you that in the matrix representation of any linear transformation, fine, if we have basis members, suppose this is the two-dimensional vector space, so we have two members in the basis. So this is the coordinate vector with respect to the basis B, and this is the second, it means V2, T of V2 coordinate vector with respect to B, right? I hope now you people understand. Fine. So here what we are getting is that we can write it down like this. So it means this member is representing this value and this member is representing this value. Fine. You can use this way also. So any member x comma y will be written as x times 1 comma 0 plus y times 0 comma 1. Fine. Now what you can do is that t of x comma y as what? Now you will use the property of linear transformation. I hope all of you know that t of alpha u plus beta v is equal to alpha times t of u plus beta times t of v, right? So here alpha is your x, beta is your y, u is your 1 comma 0 and v is your 0 1. So I just applied that property. And the important thing here is that t of v1, that is what you got here is that t of 1 0, suppose I am saying here, because we have v1 member as 1 0. There is a very important thing that you need to understand. What is that important thing? Suppose this came out to be any general vector, okay? Suppose this came out to be any general vector a comma b, fine. And you know that if you want to find out the coordinate vector with respect to the standard basis, you will write it down like this now. See? So if I ask you the coordinate vector of 1 0, what it is going to be? It is going to be AB, right? AB only. So what I am telling you is that the coordinate vector of any vector with respect to the standard basis is that vector itself. And if you still didn't get that point, I will explain you once again with the help of an example. Suppose you have a member 2 comma 3 from the vector space R2 and you have the standard basis, okay? And I asked you to find out the coordinate vector with respect to basis B of this vector V. What you will do? You will write it down like this: 2 times 1 0 plus 3 times 0 1. And this is what? You will put these scalars in column na? See? And this is what? This is your vector V itself na? That's why I'm telling you with respect to standard basis, the coordinate vector of any vector is the vector itself when it comes to the standard basis. Fine. So this is what we have to do here. With respect to standard basis, the coordinate vector is same na? So you can keep here what? 2 minus 1. And then you can keep here what? T of 1 0 is going to be equal to T of 1 0's coordinate vector with respect to B, 3 2. So what you got? 2x plus 3y, and here you are getting minus x plus 2y. See, you are getting the same result. So either you can use your basic concept or you can use the trick. Both the ways you can get your answer. Fine. So let's proceed to a few more questions that we will cover today. Okay, so the next question that we are going to do is T from R2 to R2, and in this question I will tell you the application of matrix representation, and in the next lecture we will cover few PYQs which will actually the application part of this series that is going on. So suppose we took it like x minus 5, fine. So yesterday I gave you a hint why this is very important. Matrix representation of any linear transformation is why this is very important. So I told you that if you want to find out, if you want to find out the suppose this is T from V to W or V to V anything, and you want somebody ask you find out the determinant of T, or somebody ask you find out the trace of T, or somebody tells you to find out the rank of T, eigenvalues of T, then what you will do? So in the last class I told you that somewhere it is a little bit complicated task for you to go through the definition of LT to find out all these things. So the way you proceed is that you try to find out the matrix representation in case if it is linear operator, or like this the question that we did just few minutes back, either you do it like a linear operator or a linear transformation, you find out the matrix representation. So now you have a matrix in your hand, fine. Either it is of if it is a linear operator then it would be of n cross n, or somewhere like this. Suppose I am talking about this only this time, okay, let's not talk about this for a few minutes. So what you will do is that now you can find out the determinant of A, and that will be equals to determinant of T. You find out the rank of A. Rank of A matrix is going to be the rank of linear transformation T. Eigenvalues of the matrix A is going to be equals to the eigenvalues of linear transformation T. Determinant of this A matrix A is going to be determinant of this linear transformation T. See how useful this topic is. If you want to know something about this linear transformation, just know everything about its matrix representation. Once you will be able to know everything about its matrix representation, you will be able to answer every question about this LT. That's what the beauty of this topic is. That's why I'm teaching you so thoroughly. Okay. So, but the point here is that in our last class also and in this class also, I told you one thing. Suppose we have a basis B1, then this is going to be a different matrix. Suppose we have a basis B2, then we are going to have a different matrix. And इतना प्रॉब्लम वाली कोई बात नहीं है, हमने अभी एक क्वेश्चन किया है थोड़ी देर पहले. Let me just give you, yeah, see this one. We have T from R2 to R2, T of x comma y was x plus y comma x minus y, where this was the basis. Then we got this as the matrix, suppose this is A. And then in the same question I give you standard basis, the matrix that we are getting is this. See, both the matrices are different. So there might be a question in your mind कि ये इतना application तो इसका बहुत अच्छा है कि भाई एक का डिटर्मिनेंट निकालो, LT का डिटर्मिनेंट बता पा रहे हो, रैंक निकालो उसकी रैंक पे. बट व्हाट अबाउट दिस कॉन्सेप्ट? सपोज मैंने किसी बेसिस से निकाला मैट्रिक्स ए आई, किसी और ने बेसिस से निकाला तो मैट्रिक्स कुछ और आएगी. What is the guarantee that both the matrices will give us the same property? So this is a very important thing. So what you need to know about this topic is that कि आप किसी भी बेसिस से मैट्रिक्स बनाओ, ये जो मैट्रिक्स आपस में बनती हैं ये कैसी होती हैं, ये हमारे पास सिमिलर होती हैं. यानी कि अगर आप चाहे तो B1 के रिस्पेक्ट में निकालो, या आप B2 के रिस्पेक्ट में निकालो, या आप B3 के रिस्पेक्ट में निकालो, ऐसे आप कितनी भी बेसिस के रिस्पेक्ट में निकालते चले जाओ, सारी मैट्रिक्स जो होती हैं वो सिमिलर होती हैं. और आपको सिमिलर मैट्राइसिस की प्रॉपर्टीज़ पता है कि उनका डिटर्मिनेंट सेम होगा, ट्रेस सेम होगा, आइगन वैल्यू सेम होगी, एंड देन ट्रेस सेम होगा, बहुत सारी प्रॉपर्टीज सेम होती हैं. तो बस यही काम करना है हमको. अब आप पूछोगे कि मैम आपने वो ट्रिक क्यों पढ़ाई थी? वो मैंने आपको इसलिए पढ़ाई थी. सोचो, ये आपको दिया है। एंड अगर मैं आपसे कहती हूँ कि डिटर्मिनेंट ऑफ टी निकालो, है ना, देन आई आस्क यू ट्रेस ऑफ टी निकालो, देन व्हाट यू विल डू इज दैट, बिकॉज वी नो दैट हम किसी भी बेसिस के रिस्पेक्ट में अगर मैट्रिक्स बना रहे हैं वो सारी सिमिलर है, तो कॉम्प्लिकेटेड मेथड को क्यों यूज करना, वाई टू गो फॉर अनदर बेसिस, गो फॉर द सिंपलर वन, स्टैंडर्ड बेसिस, like I am using 1001, okay, and again I told you कि if we are going to find out the matrix representation with respect to standard basis, first component will give you first row, second component will give you second row, here is the matrix. And now what you will do, determinant of A is what, this is -1, this is going to be determinant of T. Suppose somebody asks you what is the trace of T, you will find out the trace of A matrix, that is 0. Somebody asks you about the eigenvalues, which I will teach you later on, since it is a lower triangular matrix, so 1 and -1 are going to be the eigenvalues of A, so these are the going to be eigenvalues of T also. See, this is so simple. This is the application part for this topic, that if you want to do something about this LT, do something about the matrix. And now, just to prove that whatever I am saying is correct or not, suppose I am considering another basis B2, which is 1 0 and 1 1, okay, and then here we are using the same linear transformation T of x comma y as your x comma x minus y, okay. Let's do it with the help of another basis also. So just simply write down one member in general in terms of linear combination of basis member. This is your C1 plus C2, and this is nothing but your C2, this is x comma y. So you are getting C2 as y and C1 as x minus y. So here you got x minus y as x minus y times 1 comma 0, plus you got y times 1 comma 1, okay. And if you want, you can check it once also that you are getting right or not. So you evaluated T of 1 0 by what, by using this definition. So you are getting 1, and 1 minus 0 is 1, so write it down like this. So this is 0 times 1 0, and then 1 times 1 1. Next what you have to find out is T of 1 1. What you are getting, T of 1 1, x and x minus y, this is 0, this is x minus y, 1 times 1 0, and then you are getting 0 times 1 1. Form the matrix by taking the transpose. What you are getting here is that this is your 0 1 1 0. Now you see one thing, suppose this was your B2 B matrix. Now you find out the determinant of B, what it is coming, -1. You find out the trace of this matrix B, what it is, 0. You find out the eigenvalues. इतना तो सबको ही पता होगा आइगन वैल्यूज हम कैसे निकालते हैं. तो दिस इज लैम्डा स्क्वायर -1 इक्वल टू 0. इफ यू आर गोइंग टू फाइंड आउट द कैरेक्टरिस्टिक इक्वेशन, इट्स प्लस -1. So eigen values for this matrix B is what, 1 -1. Fine. So all these things, and rank we are getting 2. And see the previous one, determinant -1 -1, we got trace 0, here we got trace 0, we got eigenvalue 1 -1, we got eigenvalue 1 -1, rank is 2, again here rank is 2. See how simple it is. So it means if in the exam we have been asked to find out anything about this T, either about its trace or about its rank, suppose, then if somebody asks you about determinant or eigenvalues, anything, what you will do, you know how to find out the matrix representation with respect to any basis, but which basis is making our work easier and simpler, that is the standard basis. हम अपनी ट्रिक लगाएंगे, मैट्रिक्स बना देंगे, सारी इन्फॉर्मेशन को दे देंगे, ओके. सो दैट्स इट अबाउट दिस क्लास, एंड आई होप कि आपको इसका एप्लीकेशन पार्ट बहुत अच्छे से समझ आया हो. इस पे हम कुछ और प्रैक्टिस सेशंस भी करेंगे. लेट्स वेट फॉर द अदर सेशंस एज वेल. थैंक यू सो मच.